about process and thread affinity on KNL nodes. So we think that the correct affinity settings are the base for getting your optimal performance. By all means, we want avoid oversubscription of the cores and threads. And also, it is a guidance for getting your optimizations, checking your performance, whether you're doing the right going to the right direction of your getting your code optimized. Also, one of the goals is also to promote OpenMP standard for portability purpose to instead of these Intel specific or Cray compiler specific settings, etc. And on KNL nodes, besides CPU, normal CPU binding, there are also memory binding concerns as well. So let's list the features that will affect our affinity settings. There are different cluster modes. There's no subnumeric domains, several of them, and there are cluster modes that with subnumeric domains we need to consider. And for memory modes, there's also the cache modes. Just put it up there. Hybrid that we call them extra numeric domains, but with no CPUs. And also number of cores per node. Some of the parts has 64 cores, some of them have 68 cores. These are things that will affect our affinity settings. So I want to introduce two handy tools that give you a nice idea of how the cores and threads are laid out. One of them is HFLC-LS. From here, you can see that say core 0 and core 1 actually share a tile. You never want multiple MPI tasks to share a tile cross boundary. And you can see the list of numeric domains, and for each core, it lists its physical core and the logical core numbers for that. And the next tool is numCTL hardware, -- hardware or -h. And I just list two examples here. This is a SNC4 in cache mode, and tells you that it has 4 numeric domains, 0, 1, 2, 3, and a list number of CPUs. You can see that there are 18 cores each for the first 2 domains and 16 cores each for the next 2 domains. This is on a 68 core node. And it's a cache mode, and there's only 4 of them, and it lists the numeric distances. For the OpenMP concerns, you want to make sure you are on your correct numeric domains for the memory allocation. And this is another example with 68 core quad flat node. So now all the 68 cores are on the same numeric domain, and lists all the physical cores plus all the logical cores belongs to that. And the numeric domain 1 has no CPUs at all. This is the HBM. So now let's say we have a 68 core KNL node. I want to run 16 MPI tasks with 8 OpenMP threads per task. This is the usual way. With OpenMP, you want to set number of threads, and you want to proc bind to spread out, and then you want to set OMP places to threads. There are other choices, but these are more recommended way of setting them. Now you run it with 16 MPI tasks. What do we get? XTHI is one of the sample test code that I routinely used to verify my correctness of the affinity settings. So here, it tells you from all binding to all these affinities. Is this correct? Okay, let's plot this out. Now, what do you get? I only masked, colorized the first 6 MPI tasks only, and one unique task means 1 MPI domain. And so here you have 8 threads right here, and second MPI domains like that. Green one is the third one. So say for physical core 4, let's look at physical core 8 and 9. You can see 8 and 9 actually share a tile, but they are on 8, you see different MPI tasks on it. That's just a total mess of the binding, and performance won't be good from there. So how do we fix this problem? First, let's find out why it's causing that. The reason is that because your number of MPI tasks is not divisible by 68, and the MPI runtime, basically, Intel MPI runtime gives you, for each MPI domain size, is the number of logical core is by 68 cores times 4 hyperthreads, which is 272 divided by your 16. That's how it messed up. So what we do, let's manually set it by on purposely waste the extra 4 cores. So now we set it to MPI ping domain, which is the size, to 256 divided by number of MPI tasks, which is 16, and it gives you the number of 16. So this is essential for on a 68-core KNL nodes if your MPI number of tasks is not divisible by 68. If it is, or if you are on 64 cores, it's okay to not set that. And then with Slurm, we have this Cray and pitch. There's a way of doing equivalent of that flag is -C. Is also, we can set that to number of logical cores. And for Slurm, this -C is needed for both 64 core or 68 cores. You always have to set number of logical cores for that. Now let's plot this, the MPI domains and threads affinity bindings. They're all very neatly aligned. And in this case, when I set that, it's by default, it will waste the last 4 physical cores. And another example with SNC4 cache node. With Slurm, we set -C number of logical cores, and it's also neat. And with that, it will actually not to use the 2 extra cores on the first and second NUMA domains by default. And I learned yesterday from TAC, there's another way of doing that by using an IMPI ping processor exclude list. Here, for the SNC4, you would exclude like 16 and 17, and list all the logic codes for that as well. We have 16, 17, and 34, 35, along with all the logical cores. And this will achieve the same affinity as in this previous slide. And for the quad core, by using this exclude list, there's also a way of you can control whichever task, whichever CPU core you want to exclude. Instead of, when I do IMPI ping domain, it's always exclude the last 4 physical cores. Here, you want to do where you want to do it, but always make sure when you exclude them, exclude in pairs. Just throwing in one slide of memory binding. So memory binding, basically you treat in flat mode, in quad mode, say quad flat, the NUMA domain 1 is the HBM. And in SNC4 flat, NUMA domain 5, 4, 5, 6, 7 are the HBM. So you can use NUMA control -M option. M is force binding, and it fails if your memory footprint is over the size of HBM. So you can use a NUMA control -M option in MPI run options or in Slurm options. They both support that. In SNC4, the memory domain 4, 5, 6, or 7, you want to distribute them. So if you're running a 16 MPI tasks, you would do 4 of them to bind them to memory domain 4, and then another 4 to 5, etc. And then if your memory actually footprint is over the HBM, there's another option with NUMA control. You can use --preferred, so that it'll overflow to DDR if it's not, it does not fit in HBM. With Slurm, there's also, besides CPU bind, you can use a mem bind option, and you can map out memory binding. So this example, the 16 MPI tasks, it does actually, you list for each of the MPI tasks, which NUMA domain, NUMA domain, actually the HBM domain you want to bind to. So the first 4 you bind to 4, first 5, the second 4 you bind to 5, etc. However, in Slurm, there's no preferred option. It's always forced, it'll fail if it doesn't fit. So in those cases, we recommend people can use the NUMA control instead of mem bind. For nested OpenMP, it's also, again, this number of logical cores per MPI domain is essential. And then the way of doing that is very similar as all OpenMP standard ways. And then for the proc bind, you want to do outer loop as a spread and inner loop as close. And you want to set the nested equals true, and ping domain is, again, the logical size. There are 2 Intel MPI hot teams and hot team max levels is helpful for keeping the threads alive. And then because you don't have nested OpenMP everywhere in your code, so what I suggest is that wherever you have nested OpenMP, those regions use number of threads clause in your setting. And then for the other non-nested regions, So you don't want to set num threads everywhere to save your work. So you can use the OMP num threads environment variable to do that. I just want give you actually all this motive for those work. How do we discover MPI pin domain, etc.? It's actually from a real application work. We started from giving, they have nested OpenMP, and then I gave them recommendations. Let's start with OpenMP settings. And turns out, with giving them OpenMP settings, they're not getting the same performance as with the KNP settings. So that really bothers me. I tried to investigate what's going on. So I put together 7 example cases like that, and with 7 examples here, working with Intel people as well, we expect this to see same results because they are either KNP or OpenMP with different compact and or scatter, but this test case is on a 64 quad flex as a start. But the real case was some of them are way slow than others. So we printed out all this thread binding in numbers, etc., and tested with a simple test code, seeing bindings are correct. We tested with another application, they're all correct. So, and after careful investigation, it seems that for this source code, even if you're asking for 2 threads, it's running with 4. So now we think something wrong is in the source code. Then checking the source code, we finally find the bug because in the source code they had set nested OpenMP is on by default. And then we're giving you when you're giving OMP num threads equals 2 without giving second level will inherit the first level. Although in their mind, in their intention was to do 2 and 1 for nested OpenMP for this test case. So after this problem is fixed, we got same performance, and the final scaling with nested OpenMP also achieved good scaling. This is my second to last thread. Basically, I wanted to throw out how do we verify our affinities? I routinely use one code from xehi.c from Cray, and I also modify it to add on nested OpenMP. So every time I have my settings, I try that, print out, see if it's correct. And then, so we know that Intel compiler has something, KNP affinity equals verbose. Cray compiler has another one, Cray OMP check affinity. So this, from our program's point of view, it's very desirable that there's some kind of standard, and this standard has to be set in OpenMP standard. If there's a way of, instead of using your sample code, we can display for real application at runtime. So I have initiated this discussion with OpenMP standard. Hopefully we can get something into it. The summary is, I want to say there are ways that nodes, different number of cores, different modes, making it hard to achieve affinity, but it's still essential to critical. And the number of logic cores per MPI task is how to get by with 68 core nodes. And I can give you my test codes if you're interested. And I've requested to OpenMP standard, the binary, the binding checkings. And want to thank lots of people for the motivation and getting this resolved. Yeah.
I have time for only one question. Well, these slides will be in the website, so I think Helen gave us a lot of examples and a good list of tricks. Thank you. So the last speaker of this lightning talks is Mora. Vamos.
Hi everyone, I'm Juliana Zamora. I work at Los Alamos National Lab, and I'm also a grad student at Georgia Tech. And today I'll be talking about effective OpenMP implementations on Intel's Knights Landing. So let me just give you an overview of what I'm going to be talking about. First, I'll talk about high-level OpenMP and the differences between that and conventional OpenMP, and why not MPI everywhere? I always get this question, you know, I hear it's good, right? Then we'll talk about the best of both worlds and future work and insights on, you know, what I was able to see, like just working on this for a few months, and how was I able to get performance increases. So conventional OpenMP, you guys, as most of you guys know, you'll have your parallel tasks that you want to put your pragmas. You know, you want to start your parallel task, your pragma starts it, and then you close it, starts it, close it, and whatever subroutine that you're doing. And that tends to have very large thread starts and thread weights. It can go up to 30% or more even. And with high-level OpenMP, you'll start your pragma in your driver class or your parent class. The threads will stay open throughout all the regions, will become dormant in regions that aren't used but will be still active, and each thread will have a specific space in memory. And with a linear map, I was able to see by doing high-level OpenMP, I get really dramatic decreases in the thread weights and thread starts down to 0.5%, an increase in performance of the whole application, which is pretty amazing. In the beginning, I was like, this isn't going to really do anything. And I started with each loop doing it. So one loop, I got like 10%. The next loop, it just kept going up, and it just became addicting. And I was like, I want to make more codes faster. So as you can see right here, this is just some pseudocode of, you know, I've been asked like, oh, what does it look like? What's the difference? So as you guys know, this would just be doing the conventional OpenMP. With parallel OpenMP, like I said, you have the threads started in the parent class, and with that, you need to have a separate subroutine that will get the thread memory addresses for each specific thread. And then your subroutine will actually have no pragmas in it, and then it will call the other subroutine that gets the thread memory addresses. And this makes your code go substantially faster. And yeah, so lower bounds and upper bounds of the threads are calculated in a separate method. So here is one of the first codes that I worked on. That was itself, it was a spectral elements libraries in Fortran. It's a spectral elements method, and I worked on a dipole example. He had it originally just in the conventional OpenMP, and he was like, oh, can you speed this up? And I was like, sure, let me try it. And then I heard about high-level OpenMP from Bob Roby and John Levesque, and I'm like, let me try this out. And I got the parallel efficiency up to 88% just by not doing any fundamental changes in the physics or the code. It was just by taking out the pragmas, seeing where the shared and private memories are. And people ask like, oh, this high-level OpenMP, is it always better than conventional OpenMP? And that's just dependent on your application. If you want to have, if you want to have good speedups, yes, but then it does take time to put it in. You have to understand like what the threads are doing in your code. You have to understand what variables are shared, which ones are private, and also, with dynamic load balancing, conventional OpenMP is easier. It gives you the option of doing that. High-level OpenMP is a little more difficult. So with that, I got more codes of people wanting me to increase their performance, and I was able to work on Clamor. I got the parallel efficiency up to 89%, and High-Grid, which, I think is it coming up? Oh no. So I think the parallel efficiency was up to 86%. And they're both comparable to MPI, which is, you know, pretty good. And so you're asking, so why not just do MPI then, right? Like, what's the point of doing this extra work with OpenMP? So with the future of computing, it seems, at least with the KNLs, and at least for now, MPI everywhere, it doesn't seem very feasible. Yes, you can do 68 ranks per node, but then you're leaving a lot of performance potential on the table because you're not using the hardware threads. If you do use all the hardware threads, you can, for this application done by Dave Nystrom, he was showing that if you use all the hardware threads, you can use up to 1/3 of the memory, and that's just using 1/4 of Trinitite. If we want to start using like thousands of nodes and I think Trinitite's going to be over 9,000 nodes. You're not really going to be. It's not really going to be possible at this point right now. I know I always like to emphasize, just in case there's a new plugin or something. Sorry, a new plugin that allows you to use MPI everywhere. But for right now, I think our motivation is to prepare for Trinity, and that's why we're looking at our MPI and OpenMP to have full CPU utilization, full hardware utilization, fix the MPI scaling issues, better memory usage, and improve performance and less contention for the network. Right now, I've been working on Trinitite, which is a test bed for Trinity. It has 100 Haswells, 100 KNLs, and mostly a lot of the work has been just done on one node, and it goes up to, some of the work goes up to 82 nodes, but that's in the appendix if we have time. I know I got in late, so everyone's ready for the break. So, and a lot of the configurations were on quad cache, that meaning MCD RAM was used as cache. So, like I said, I was using the Cray XC40 with the KNL, which has a little bit of a different terminology, so let me just go over it before I go through the results. So there are, with the Cray system, we have a J flag. So I know Helen was just talking about the exporting the proc bind, and I think there was another one. But with the J flags, it allows you to, instead of doing like proc bind, spread, or I think there was another one I forget right now, the J flags will allow you to use the hardware threads. It invokes the hardware threads. So J2 will give you 2 of the hardware threads, and J4 will give you 4 of the hardware threads. And that's just representative of one tile. So an example of my execution would be something like this. So you can understand what J4 means in this aspect. So here are with the results with the different J flags. And with MPI, you can see that it doesn't improve when you start using the hardware threads. But with OpenMP, it does improve when you're using the hardware threads. That being said, on the hybrid mode, or the MPI with OpenMP does substantially better than MPI. And here I'm just using 64 processes just to be consistent across all of them. And OpenMP, obviously, as many of you guys know, if you use too many threads and you start getting NUMA effects and it starts decreasing the performance. But this is just so it can be consistent across the comparison. And this is all comparing against serial. If I were to do the best performance hybrid, it was around 50 something speed up. But right now, just with all the same hybrid, you get up to 46, and MPI everywhere you get 30. And so with my future work, I used the CrayPat tool, the CrayPat Lite. We had a KNL seminar a few weeks ago, and they were talking about the CrayPat Lite, and it was really awesome because it showed you which parts of your code were vectorized, what parts were taking up most of the CPU time. So right now we know that stress TKNU is something that we really have to work on. And also, vTune would be good to dive in deeper into the performance, and using the roofline to chart our performance. Additionally, we have to add a lot more of a high-level OpenMP into high-grid. It's a very big code, and there are only a few routines we have it in right now. But with just even that, we get some good performance increases. We also have to improve vectorization and use some different KNL configurations. Like we didn't really do core specialization, the -R flag, and I understand that that does take up, that can lead to some memory imbalance, and we definitely need to put that in there. So some of my insights, so I've only been working on this for a few months, and I was able to work on 3 different applications. And having the use of Valgrind and a linear map and Intel Thread Inspector, those have been really useful in being able to look at these codes that were completely in different languages. They were Fortran, object-oriented Fortran, C++. Go into them within a few weeks, have some performance improvements, just because I was also just, like a linear map would tell me, hey, over here, these are taking 30% of your time. I'm like, okay, let me just work on that. And surprises were that OpenMP, for me at least, utilizes the hardware threads better than MPI, just because everyone kept telling me, just use MPI, stop worrying about OpenMP. And so it was nice to see that, and also it was nice to come here and hear a lot of people talk about OpenMP or high-level OpenMP. And that the KNL is more complex than I had anticipated, that there are many configurations that I think it became overwhelming. I'm like, which one should I do? And I just want to thank Bob Roby and Los Alamos and everyone that helped me get through several different applications and get some increase in performance. And if I do have other results from in my slides, if you guys want to see, with running on all the different configurations and how they were, I could just go right to them. So yeah, this is Mike Berry. So these are all the different configurations run. I mean, it's a little different. So he wasn't doing NC, what is that? The NUMA control, which uses the high bandwidth memory. So that's why flat is below. But I think this was after the fix. John Levesque was saying how the BIOS for SNC4 was fixed. And as you can see, SNC4 is doing better than all the other configurations. So I guess it is a good chance, it's a good time to give it a go. We were just working on mostly quad cache, so I think when I get back, we're going to start working on the SNC configurations. If you guys have any questions, let me know. Thank you. Okay, sorry for going over. Okay.
Try to use tasks as they are defined in OpenMP4. No. No. Okay. Instead
Okay.
do.
Okay. Yeah. I'll get to it.
Okay.
Okay.
Yeah. Why is the OpenMP pure OpenMP the worst?
Well, it's because of the NUMA effects. At some point, it just becomes it's just not good to like overload the so it's just on one tile or on one node, and then once you get past, I think it's just you just get all these NUMA effects, and the performance goes down a lot. So if I was, I think when we were getting the best results with 8 threads, and then it just, like I said, there's still a lot of work to do on high-grid and OpenMP, and once you start getting past 8 threads or start even going to 16 threads, it started going worse. And that wasn't just, that was from like several applications that I was looking at. But like in comparison to the older results, it was getting a better performance. But this is all just in comparison to serial right now.
Thanks again to
Thank you guys for listening.
Anna.